So how do we want to think about measures of spread? When we're describing data, and if we think about this in terms of describing data, I think that will give us a lot of context. I'll go ahead and share my screen. Now, the thing that we've been able to do in thinking about centrality is like, well, let's say we have a bunch of numeric points, and we'll just think about this in terms of numeric points. So, here, right? Just a bunch of points on this line. There's going to be some spot, right, that we can describe as being central in some way. Whether this is the median, maybe there's a very similar spot, or maybe even a very different spot that we can think of as the mean, which will usually represent as x bar or mu in, just depending on the scenario. But if we think about this kind of in a vacuum, we're only considering, a couple places, right? We're only considering one descriptor of our data, or a couple descriptors of our data. And what might be helpful is to describe maybe more how the data spreads around these points. Now, there are a number of different metrics that we can use. We're going to focus on just a couple. Primarily the IQR and the variance. We'll play around with different concepts inside of those. And when I say variance, what we'll end up focusing on or thinking about more is, say, the standard deviation. But even still, standard deviation is essentially variance. It's just the square root of the variance. So let's start with 5-number summary. I know we kind of went over this briefly last time, but I'm going to go ahead and review this and review it, similarly to what I said last time. The 5-number summary is just these 5 items. It's the minimum, the median, and the maximum, which, if you think about how we can get these, the minimum we can get in Python with the min function, maximum we can get with max, and we already have a median function, right? So we'll be utilizing code that we've already written. We're going to be using that median function from last time. So you'll want to snag that code out of the repository if you don't already have it. So we've got this median function here. And for Q1 and Q3, these are just the medians between the minimum and the median and the maximum. So Q1, Q3. And often we'll say, well, this is the 25th percentile. The median is the 50th percentile. And Q3 is the 75th percentile, which I also have noted there. Okay, so that's I should probably leave that up there, actually, since I'm going to have you code this right now. So I'll put this up here. And maybe I should keep this annotated a little bit, right? So minimum, right? We've got the min function. Maximum, we have the max function. And then for the rest of these, you're going to utilize the median function, right? So for that one and that one, obviously, and for that one, you're going to utilize the median function. Okay, so I have 5 minutes slated for this, for coding this, but this is possibly a little more challenging than that. I'm going to put 7 minutes on it just to play it safe, and then we'll walk through how to code it. Ping me in the Slack if you need the median function that we coded last time. Just give me a quick thumbs up if you need that in order to work on this breakout. Okay, I'll grab that. And you can name your function 5-number summary. Feel free to start in on it while I snag that code. Give me a thumbs up if you want 2 more minutes on this. All right, I'm going to add a little bit of time. Okay, I'm going to start coding this out. I'm sure some of you almost got there, and that's okay. This is not a super easy function to write or anything like that. We have all the tools to write it, but that doesn't mean it's easy. So I'll talk through this as I usually do, but just want to. I'll take a little bit more time with it, so that it's clear what's going on here. So the name of the function is I just deleted it, but it's a 5-number summary, right? So 5-number summary, and when I'm writing these, I always think in terms of, well, how am I, what am I putting into this function? Well, I'm just putting in a list of numbers, so I'll start with that. And there are some things that I'm going to need from this function, and it's my 3rd screen capture of the thing that I keep deleting, but I'll put that over there. And the things I can get right offhand, I'm just going to do that. I'm going to get that out of the way. And that would be the min, the max, and the median. So this is my tendency. If I'm going to call something min, I'll do min underscore. Notice min by itself is a reserved word. So min gets min of the list, right? And then max gets the max of the list. And the median gets the median of the list. So that's all pretty straightforward. Now, if we want to get Q1 and Q3, and we see those as being the median between the minimum and the median, then, well, there are a couple questions that we might need to answer, that we might need to think about here. And, we'll probably start with thinking about this in terms of the data being ordered, right? That just kind of makes sense. So if I say And when I say ordered, I just mean I'm going to sort it. So I'm going to get a sorted version of the list, which is easy. I can just do sorted list gets sorted of list. And then there's a question of, do we include the median in the data? Well, that really depends, right? If if it's an odd value, then if it's an odd length list, then we're going to have to treat this a little bit differently from an even length list. So the way I can check that, of course, is I can say, well, if the length of the list is odd, and that's what this statement says. And again, this statement is equivalent to saying if the length of the list mod 2 equals 1, well, 1 evaluates to true, so that works. Well, I'm going to get the lower half and the upper half of the data. And just to show what this might look like, I'll say lower half. And this is going to be this sorted list. And then I'm going to index this from the 0th index up until the length of the list divided by 2. And remember, length of the list divided by 2, that's going to result in a float, so I need to cast that to an integer. Now, if that's the lower half, it's easy enough to get the upper half. And I can do that like so. Let's just do upper half. And I'm going to take this and move it over, and move it over here. So we're starting at this value, right? Now, if this is an odd length list, there arises this question: do we include this median of the list in either the lower or upper half? And it turns out that we're not going to. That's just a facet of the 5-number summary. The median shouldn't be included as a value in both the top part of the upper half, the top part of the lower half and the bottom part of the upper half. There are different thoughts on this. Different people do things differently. It's people. There are other metrics that have similar kind of dilemmas, and are we going to be inclusive of this or are we not going to be inclusive of this? It doesn't really matter, but this is the more common convention. We're not going to include the median value in the lower and upper half of our data. So that should work. And then otherwise, we should do, we can say almost the exact same thing. We can construct these lower and upper halves, but instead, this time, if it's an even length list, well, then we're going to take that lower half and take that upper half. It's going to be the same amount of numbers in it, and so that'll work. And then with that, we can just, we can get Q1 out of the lower half. That's just the median of the lower half. And then Q3 is the median of the upper half. And then we can just return everything. So I'll return the min, I'll return Q1, and these should be returned in order, of course. So I'll return the median, Q3, and I'll return the max. Okay. So I think this should work, and I should probably test it with some data. Did I not define the median? I called it median, which is not a good name. So the data that I'm going to construct here, I think this is maybe a nice way to see this. I'm going to get the range from, 0 to 99. And I'll cast that as a list. Oh. Sorry, I just reset the zoom on that. Okay, I'll cast that to a list and call this sample data, and we'll just get the 5-number summary on that. So this sample data, and let's see what we get. probably an error, but, well, definitely an error because I'm seeing an error. There it is. Okay. So 0, 24.5, 49.5, 74.5, and 99. And that makes sense. That is what we would expect to see here. So notice what you might notice here is, since we're going from 0 to 99, that middle value is not 50, right? That middle value is 49.5. And that makes sense. That's not actually a data point in our materials. Now, if I take this to 101, so it's 0 to 100, then notice we're not including 50 in this 0 to, we're essentially doing 0 to 49 and then 51 to 100. So that might be a little counterintuitive given this, but it's like, are we including these values? Are we including the 25 as the 25th percentile if we have a 0 in there? Maybe not, right? So let's do this, right? It doesn't fall where you might expect it to fall, but that's due to this include or not include. Now, we could make this code a little bit simpler, right? We could get let me think about it like this. I'm going to simplify this just a little bit. So I'm going to get this even flag out of here, and ideally we're going to get the same result if I do this. So this is a nice little trick, simplifies the code a little bit, and all I've done here is even will be 1. Sorry, I should call this odd, not even. Odd will be 1 if the list length is odd, right? So we're going to add 1 or we're not in that same instance. So hopefully that makes sense. It gets takes a condition out, makes our code a little bit simpler to see. And we still get the same answer. Okay. So let me paste in this code. And let's think about how to use this 5-number summary. If you think about this, about the 5-number summary as just being, okay, well, this is just a descriptor on some data. That's easy enough. We can just describe some data with the 5-number summary. That's not a problem. What we might want to think about, though, is what we can do with that in order to procedurally figure out something like a detection of outliers. And so I'm going to work in that direction. The way that we're going to work toward that is through just thinking about what the 5-number summary is. So we've got a minimum, a maximum, and we've got our min, our max, and then we've got some median, and let's say the median is there. And we have our our Q1 and our Q3, and let's say those are there and there. This may be taking a form that you've seen before. This is actually a type of plot that we have called a box plot. And what we see is that the middle 50% of the data is here. It's Q3 minus Q1. We call that the interquartile range, or IQR. So the IQR is Q3 minus Q1. Now, this can be helpful. The IQR can be helpful if you want to automatically, if you define what an outlier is and you automatically want to detect it. So that's the lens that we'll consider the IQR in. You can use it as a descriptor for the, middle 50% of the data. That's fine. It's sort of like, it is a measure of spread, like we can see what the distance is between Q3 and Q1. Essentially, that's what we're seeing here. So I'm going to have you code the IQR, and let me give you a little bit of data to work with. So use that. Notice these are just ranges, by fives between 0 and 50 and 0 and 100. And you're going to utilize that prior function, okay, that 5-number summary function, in order to write your IQR function. So IQR is going to be dependent on it. You're going to have to call out to 5-number summary in order to solve this. Or you don't have to do that, but you should. It'll be easier. So I'm going to put 4 minutes on the timer and go ahead and solve this. Okay, so I'm going to go ahead and solve this. So the IQR is simply Q3 minus Q1. We have access to both of those, both Q3 and Q1 right here. So I'm going to end up calling out to 5-number summary in order to get, well, I don't need the min, I do need Q1, I don't need the median. I'm putting underscores here because I don't need them. I do need Q3, and I don't need the max. Okay, so I'm going to put all of this, what I get out of this, I'm going to put inside a function called IQR. And we'll return Q3 minus Q1. And so let me use the same data from above. Oh, actually, I have sample data. So I've got A and B. So why don't we use those? And we can get a sense of the, we can get a sense of the IQR from A and B. So let's see IQR of A and IQR of B. So 30 and 55. Now, why are we getting 55.0? It's due to one of these values coming back, probably the median, or sorry, probably, well, I'm not sure which one. A float with an int, right? If you perform a mathematical operation between a float and an int, you're going to get a float as a result, and that's fine. Numerically, it's not going to make a difference for what we're doing. But notice that we do have a different spread. The middle 50% of our data traverses these 30 data points in around the median between 0 and 50. So if we think about the median, or we think about the median in relation to the IQR, let's just take the median of A, and let's just take a look at that. The median is 25, and we can think of the middle 50% as being 15 above 25 and 15 below 25. So that's an easy way that we can think about that. I think, if you're in the financial world, you probably see IQR a fair amount. If you're looking at sports, you see IQR. We see box plots for sports quite a bit. But that said, the way that we're going to think about IQR right here is as a tool in outlier detection. And it's not the only way to think about it, but it's the way we're going to think about it here. So the way that I'm going to think about outliers, if I'm going to think about this programmatically, if I'm going to think about this systematically, let's say we have the IQR, right? We have some IQR of, say, 30, like what we just saw. If we have a value in our data set that is, let's say, 1.5 times the IQR below Q1, right? Q1 minus 1.5 times the IQR. Then we can say, we can decide, let me say that, we can decide, this isn't definitive, but we can decide that, maybe we'll call that an outlier. Now, the other thing we can say is that if we have 1.5 times the IQR above, should be a plus, above Q3, then we can also say that is an outlier. Now, this is, I don't know if it's obvious, this is sort of arbitrary. We're just making a decision about this. We're saying 1.5, and 1.5 is what I'm going to call here an outlier coefficient. okay? This is something we decide. It's a little arbitrary. And we want to decide this in relation to our data. So we want to be critical about it. We want to think about it. And, with that, though, it's not necessarily, we don't necessarily want to remove outliers that we detect. We might not want to do that. It really depends on the situation. It depends on our data. It depends on how we sample. It depends on a number of things. And there might be types of data where instead of 1.5 times the IQR, we want to do 2.5 or 7 times the IQR. And this has to do with, scale, right? How does our data scale? Although at some point, we might want to, transform our data using a log scale or something like that. But in this instance, let's imagine we're not going to transform our data and we're just going to use it kind of out of the box. This is this is a generally accepted coefficient, 1.5 times the IQR. So, Q1 minus 1.5 times the IQR is an outlier. Q3 plus 1.5 times the IQR is an outlier. And with that in mind, we can write a function, okay? I'll snag this and just, keep it up in the corner if you need to reference it. And you need the IQR code, which is, of course, dependent on the 5-number summary. So, so you have that. And I'm going to have you code a detect outliers function. And let me give you a little starter code for that, in fact. So that's your starter code. You don't necessarily have to use the outlier coefficient or make it variable, although I think with that starter code it's actually just easier to do that. And here's the description of the problem. So let's do 6 minutes on this. Yeah, let's do 6 minutes. Okay, so you can, if you want, allow this outlier coefficient to be changed in order to return the outliers. Notice that you are collecting the outliers of a list into a new list, right? That's something that I want to point out. And let me give you a little bit of test code here as well. I think that'll help. So here are a couple lists here is a list that you can use to test your code. Okay, go ahead and start the timer and go for it. Okay. If anybody's still working on this and you want a couple more minutes, let me know. I noticed people aren't getting to solutions on these. So I'm a little curious if you're waiting, if many of you are waiting for me to code to see how to do this. If that's the case, that's okay. We can take a little more time with things. But if that is the case, let me know. Just say something really quick about it. If you want a couple more minutes, give me a quick thumbs up, and we can definitely do that. Otherwise, I'll go ahead and start coding. Yeah, for sure. I mean, and the expectation here isn't necessarily that, oh, hey, you should be able to code this right now. It isn't that. But I think it's also like I'll likely shorten some of these breakout times a little bit and get to coding a little bit quicker, just so that we're not all waiting. I know some of you are working on the code, and then others are waiting, and I want to try to balance that pretty well. Okay, so I'm going to go ahead and code this out. And as I said, this is going to be dependent on my IQR function. And it's also going to be dependent on the 5-number summaries function. So let me make this a little bit bigger. So we're calling this detect outliers, and we're passing in a list. And remember, I put in this this outlier coefficient, which by default is 1.5, and that's just to reflect the convention for outlier detection. Okay, so we want to return a list of outliers from that list that we pass in. Now, I'm going to borrow some code from up here. I'm just going to grab this. That's our 5-number summary. And we are going to need Q1 and Q3 out of that. Now, that may seem like some repeated code, something like that, but it's fine. We're not losing anything in that. I'm going to get the IQR. And in this case, I'm calling it IQR underscore because our function name is IQR. So that's just an easy convention. Not everybody follows that in the Python world. It's a convention that I definitely have adopted. Okay, so I'm going to collect outliers into this list. So I'm going to make an empty list to do that. And I'm going to say for each number in our original list, right? For each number in this list that we pass in as an argument, I'm going to see if these numbers are outliers, and that's just going to be a couple conditions, right? And this is going to be a little different from how maybe you've thought about conditions so far. There are 3 possibilities, okay? There's the possibility of a number being a low outlier, as in it's less than 1.5 times the IQR below the Q1, or an upper outlier, like a high outlier, which is going to be 1.5 times the IQR above Q3. And in either of those cases, we're going to append it to this outliers list. Because of that, I'm not going to do an if-else or an if-elif. I'm just going to do 2 if statements, actually, and they're going to be very similar. So if the number is less than Q1, and this is just a direct translation of that formula over there, Q1 minus the outlier coefficient times the IQR that we discerned. If that's the case, we can say outliers.append, and we can append the number. And the other case of this will be if the number is above Q3 by too much, right? By this operation. So that's just 2 simple if statements, and then we can return these outliers. And I think I have some, let me grab that. Grab this. Okay, so we've got these test outliers, and this is just range 0 to 100, and then I'm appending the number 10,000 on the end of that, just to be extreme about what our outlier is. And I can print detect outliers here. This will be I'll pass in our test outliers, and we can just use the default value, but I'm putting it in there just to show something. Okay. Oh, what happened? Number is less than Q3. There we go. Had a logical error in there. Let's try that again. Yeah, and the only thing we would expect to collect is this 10,000. And indeed, we collect that 10,000. So we can see that that works. Now, there might be a question of, okay, well, what if we have this higher outlier coefficient? Well, 7.5 is an outlier coefficient, still collects 10,000, and that's fine. We could play around with this more. We can tell stories about this data and change it in some way to, not collect 10,000 based on the story we tell. But again, this is an arbitrary value of 1.5. Arbitrary, not for no reason arbitrary, but arbitrary in the sense of, it's a convention and it is variable. It is something that you can change. So I put that solution in the Slack, and let's think about this a little bit further. So let's write another related function. So I'm going to write a function not called detect outliers, but remove outliers. And I think we can just use this same, test data here. And we'll kind of, because if we want to have an automatic process for removing outliers from some data, well, we don't just want to detect it, we want to remove it. So I'm going to code through this and just show you what I mean. So we can define something called remove outliers. Let me answer this question. In the print statement, I don't have to say outlier coefficient gets 2.5. I can just do yes, that is true. Yeah, just to be clear, I don't have to do this outlier coefficient gets 1.5 or 2.5 or whatever it is. I could just put 1.5 in there. That would be fine. That totally works. The reason I personally do this is for readability. If there's something, if there's a function that I'm using where there's a parameter that has a default value that's going to mostly be default, and I'm going to change it for some reason, I'll put the name in there just so somebody who's reading my code, or me actually, so I know what that is. But you don't have to put that in there. That's not required. Okay, so let's continue with this idea of removing outliers, a function to remove outliers. This is going to be pretty straightforward. It's not too different from the prior function. And it is dependent on the prior function. So we're going to be collecting, but in a different way. And I'm still going to define this outlier coefficient because it's still relevant. And I'm going to collect the outliers using that detect outliers function. And I can pass in these values. And then, I'm not sure why, oh, there we go. And I'm going to just make something called output, right? Just a collector called output. And when I say collector, I just mean an accumulator that's a list or a dictionary or some data structure that collects things, right? So I have this collector called output. I'm going to say for each number in this list that we pass in, if the number is not in our outliers, then I'm going to say output.append. I'm going to append that number. So I could do this in a couple different ways. This isn't the only way to do this. I could instead take our list, make a copy of it, and then remove items from it. That would be completely legitimate. It would be the kind of the inverse operation, but that leads to the same result. I'm taking an additive approach instead of a reductive approach in this case. And it's not that this way is better by any means. It's an equivalent operation. In fact, if we think about it, there's a slightly better operation in the reductive approach. So I'll rewrite this in a reductive approach just to show you what I mean. And I actually have the house prices data here that from last class. So I'm going to use that. And remember, this 1.2, essentially $1.3 million house. We talked about, well, should we think about that as an outlier? Is that something we should include? Should it affect our data? If we're being systematic in this specific way, we're likely going to remove that data point. So let's remove outliers, and I'll just print the list that we returned from that. And notice that we've gotten rid of a couple things. Actually, we got rid of 350, 408, and $1.3 million house. So those all qualified as outliers in the context of this data. So let me rewrite this a little bit. I'll come back to that in just a second, yes. So this is the additive approach, and I'll paste this in, and then I'm going to rewrite this to be a reductive approach, and we'll see it that way as well. This is just to kind of give a seed to the thought of slightly improved algorithms. You do not need to write improved algorithms at this stage, just to be honest. It's more about getting to a solution. It's not about getting the best solution. So if I want to take a reductive approach instead of the additive approach that I've done here, the first thing I'm going to do is I'm going to make a copy of this list. So list.copy. And, I could just call this output. Why not? So I'm not modifying the original list. That's why I'm doing this. And instead of looking for each number in the list, I'm going to look for each number in the outliers, okay? The reason being, the reason why this is going to be a little bit better is that there's going to be less numbers in the outliers, obviously, than there are in the original list. So this for loop will perform less operations. So instead of saying if the number is not in the outliers, I'm going to say if the number is in the output, then I'm going to say output.remove that number, and I should get the same result. And I do. So in this case, that reductive approach is a little bit, it's less operations, it's less for loops. And in general, if you can perform less for loops, that's going to be better, but it doesn't need to be better at this stage, just to be clear. But I just wanted to show you a different way that you could solve this. That would be completely legitimate. Okay. So that kind of gets us through the, maybe the median-based measure of spread that we're considering, which is IQR. There are other measurements that we could use for variance that we're not going to look at here. Instead, we're going to move to what I'm going to think of as the mean-based measure of spread, which is variance. So let's take a 5-minute break. Actually, let's make that 5 minutes. And I'll see y'all back here, and we'll get started on variance. Oh, yeah, and I'll answer that question. Sorry, I'll answer the question that was asked in the Slack right when we get back. So I'll see y'all back here in 5. Okay, so we're going to start looking at variance. Oh, after I answer this question. In the last example, what is the second test data statement? Yes, this test outliers.append 10,000. This convention right here, 10 underscore 000 means 10,000. Since we can't do this, 10 comma 000, we do this. That's just to make it more readable, right? Right, here's 10 million, etc. Right? That's why that's like that. So when you deal with numbers larger than, larger than 1,000, I would say, if you throw an underscore in there, it just makes it a little more readable. Okay, so let's talk about variance a little bit. Variance is pretty straightforward, and it's kind of spread based on the mean. Okay, it's the average squared distance between each data point and the mean. Now, what do we mean by that? Well, if it's the average squared distance, then if it's an average, well, we're going to deal with 1 over n, right? Because that's an average, okay? And if it's the average of each squared distance between each data point and the mean, then maybe what we can do is say, well, we have this data set. A is, 30, 40, and so on. There's a bunch of data in there. We can say that this is going to be a sum from, let's call this I equals 1 up until n of the squared distance. Okay, so we're going to measure some distance here, square it, squared distance, between each data point and the mean. A sub I minus the mean, which I'll call mu here. Okay, this is the variance. It turns out this is actually the population variance. So if we're dealing with a population, this is what our formula looks like. So, what symbols do we use for this? In general, when we're dealing with a population, we're going to use a Greek symbol. In that case, or in this case, it's going to be sigma, this lowercase sigma, squared. So sigma squared is 1 over n multiplied by the sum of the squared distances between each data point in some collection of data and the mean. Okay, so this is the population variance. We're going to do something slightly different for the sample variance. Okay. One thing that we are going to do different is we're going to call it something different. We're going to call it s squared. Right? We're going to use a Latin letter instead of a Greek letter for this because it's a sample. And everything here is going to stay the same, right? We're still going to do this, or most of this is going to stay the same, this section specifically, right? So, right, this is the sum from the first data point to the last data point. The difference between each data point and the mean. This time we'll call the mean x bar, and we're squaring that difference. The thing that's going to be, that we're going to do slightly differently in the sample variance is we're going to subtract 1 here. Okay? And I'm gonna try to give a intuition as to why we would do this. So we're going to divide by a slightly smaller number. Notice that's what we're doing. We're making that number slightly smaller, and that's what we're dividing by. Okay. Now there are reasons for this. I would say there are some interesting reasons for this, and we'll think about that. Maybe with a little bit of depth, not a whole lot of depth. So I'm going to clear that. And, oh, you know what? Here, I'll put these formulas up here in the top right, just so we have them as reference. In this case, I'm using x sub I, not a sub I. Same difference, right? We could have a data set that is x, not a. Okay, so why do we do this n minus 1? Well, first off, we call this Bessel's correction, okay? It's one of those trivia questions, you know, that you might get in an interview. What is Bessel's correction? Or why do we use Bessel's correction? So this goes back to sampling, okay? Like, you remember when we're talking about sampling, okay, here's our pool of data, and we're sampling, you know, we're sampling from this pool of data. Whenever we sample, we have the potential to miss something, right? We have the potential to miss something that is meaningful, in fact. And if you think about the operation up here in the sample form of this variance formula, if we look at this, just notice that x bar is not the population mean, right? It's not the population mean. And maybe that goes without saying, but that's important in the understanding of what's going on here. And whenever I resize this and I've drawn on it, it gives me a whole bunch of arrows, but it doesn't hurt it in that situation, so that's fine. So imagine that we've got this spread of data, right? And this is a single sample, right? And the first time we sample, our x bar lands right here. The next time we sample, our x bar lands up here. The next time we sample, our x bar lands down here. And every time we sample, we're taking the same number of samples. And you would think, okay, well, maybe we can average these. Maybe we can average these and get something that we can sort of consider to be pseudo mu, right? Something that is like a better x bar. And that would give us some better result of the variance. And maybe we could use, in that instance, the population variance formula. But instead, the way we're going to think about this is that there is some spread around this, right? And our hope is that we are going to capture mu, okay, in the spread around x bar. But what if we don't, right? What if mu is over here? What if mu is just outside of the sample x bars that we've gotten? There is that possibility. So one of the ways that we can think about this is that when we're getting a variance, right? Just to be safe, we're going to try to expand out our variance, and that's where that 1 over n minus 1 kind of comes from. It's to make sure that we are effectively capturing the variance around x bar, okay? And if you think about the variance as being the spread, the variance is related to a specific calculation of the mean. So if this variance is related to this calculation of the mean, and this x bar is a little bit higher than this x bar, well, the resulting value here is going to change. The resulting values in our summation are going to change. And this is just kind of like playing it safe. The way that we describe this is it removes some kind of bias, okay? Or it decreases the bias of our calculation. And this is one of those words that comes up a lot. Now, what do we think about bias when we think about people? We think about it as being opinionated in some way. and maybe having an opinion that's not correct at times, right? So all this means is that if we don't perform correction, then our formula might be a little over opinionated about what our variance is, and that's going to be because maybe we haven't effectively captured our mean, or part of the reason is that we haven't effectively captured our mean, or we're measuring the variance in relation to an x bar that may be a little more extreme than we want, okay, when related to the actual population parameters. So one thing Bessel's correction is not explicitly is that, remember with mean, our hope is that we can move x bar, that we can estimate an x bar that is as close to the population parameter as possible, right? That's our hope. That's not necessarily what we're going for with Bessel's correction, right? The way that we get x bar close to mu is we sample a bunch of times. We sample, we average our resulting x bars. That's one way that we can do it. Or we just measure everything. We add more data. You know, there's a number of ways we can do that. In this case, Bessel's correction, just to be clear, and this is a common misconception, a very understandable one, Bessel's correction is not necessarily about getting s squared closer to sigma squared. It's not necessarily about that. Okay? It is about capturing a reasonable variance and not excluding values that we would assume to be in the variance. So we are sort of growing the variance a little bit to be safe. So that's a little bit of, maybe a little bit of a rabbit hole, but at the end of the day, it's good to dig into these things because it may not seem like it, but that is actually an ongoing discussion. It may seem like, okay, we're just in basic statistics, but there is a lot of talk to this day about Bessel's correction and when and where you should use it, or even if you should use it in a lot of cases. So, I just want to like give a clear sense that you can go out in the world and research these things. There's a great thread on Stack Overflow actually about Bessel's correction, and here's why we use it in variance, and here's why maybe it doesn't matter in standard deviation, and right, there's like all these interesting things about that. Okay, so let's have a quick breakout. I want you to code the variance function, and notice we've got these two formulas, and they're going to operate slightly different from each other, right? The only difference is this n-1 versus n, okay? So it's not that different, but you probably want a parameter to your function that says this is a population. So by default, population would be false, right? Or sample would be true, whatever you want to name it. I have 4 minutes on here. Let's see. Yeah, let's just do 4 minutes. You're just, notice the dependency here. You're going to need to get the mean, right? You're going to need to get the mean in this function. And then you're going to need to, when you see a sigma like this, capital sigma, this summation symbol, when I say that, just to be very clear, talking about that big E, right? When you see that, that kind of indicates a for loop, doesn't it? That's kind of what that means. It means that you're going to look at every data point and compare it to something, and you're going to accumulate those values, add them up, and then divide by the number of values that you've been looking at in that for loop. So I just want to be clear about that if I haven't explained that. So let's put 4 minutes on the timer. Let's put 4 minutes on the timer, and feel free to use any of the prior sample lists in order to test this as you go. Okay, so let's go through a solution for this. Just put this over here. All right, so naming this variance, and we're passing in a list as we have been doing with really all of these. And I'm going to assume that we're dealing with a sample, okay? That's generally going to be the case. We're almost always going to be dealing with a sample, rarely with a population. So the mean is just, well, that's easy. I can just get the mean from the list from using the mean function that was defined earlier. And I'm going to define an accumulator here called total. I'm going to say for each item in the list, the total is going to be incremented by that item minus the mean, right? So this is just directly a direct parallel to our operation here. So our for loop is sort of this, summation symbol, and then we're simply squaring the differences between each item in the list and the mean itself. Okay, so we do that, and then we're going to do something different if it's a sample from a population, right? So I'm going to say if sample, I can say return total divided by the length of the list minus 1. Otherwise, we can just return the total or divided by the length of the list. So that'll work, but what I'm going to do instead is simplify this just a little bit using the trick that I showed before, which is just the length of the list minus sample, okay? And, okay, well, how does that work, right? If sample's a Boolean, why would that work? Well, it turns out that, oh, oops, this is not, oh, there we go. If sample is true will be treated as a 1. And I just to show you what I mean, I can say 27 plus true, and that'll give me 28. 27 minus true will give me, obviously, 26. 27 minus false will give me 27, because false gets interpreted, in this case, as a 0. So this is just a simple, I don't know, we call this syntactic sugar. We can just subtract subtract a Boolean as if it's an integer, and I think that's kind of nice. So let's look up here. Let's consider the variance of B, and I will paste this in. Okay, so let's consider the variance of B, and we'll just look at it, right? Actually, maybe I'll print out B, and then I'll print the variance of B, and we're assuming it's a sample, okay? Well, on first run, let's assume it's a sample, and then let's look at it again as if it's a population. We'll just think about it as either of those things. Okay. So let me make this a little bit bigger. The 0, 5, 10, all the way up through 100. And we get these numbers that might be a little hard to interpret, okay? And this is an issue in variance, or with variance. What does it mean to have a variance of 962.5? How do we relate that back to our actual numbers that we're seeing here? And just offhand, the way I'm going to say that is that's not easy. That's not intuitive. And in a sense, well, I think clearly variance is not a very interpretable, immediately interpretable metric. Why is it not interpretable? Because it's the square of something. It's like, when you describe a room to somebody, the size of a room, and you say, well, it's like, 20 feet by 10 feet. 20 feet by 10 feet, you can picture that in your head. You draw a wall and you draw another wall, and you're like, oh, okay, well, I think I can imagine that. When you tell somebody it's 200 square feet, what is 200 square feet compared to, 300 square feet? It's harder to conceptualize that unless you work in those units all the time. And I would say the same is true for variance. Variance makes a lot more sense when you work in it all the time. But what's a little nicer than that? A little bit nicer, since we're dealing with squares. We could just take the square root of this. And that's going to give us something that's a little easier to interpret. And, when we look at this, well, that kind of makes sense, right? That looks a lot like the IQR even, right? That's interpretable. That's sort of like the middle of our, the middle 50% of our data is what that looks like. That, I think that metric is a little bit better. And in fact, that metric is a thing that we call standard deviation. So the relationship between variance and standard deviation is actually that standard deviation is just the square root of the variance. And, with that, that's easy. That's a super easy function to write. I can just take the variance. I'll go ahead and define a standard deviation function and call this stdev. I'm just going to return the variance, the square root of the variance. I'll use the square root function because I think it's a little bit better to use that, honestly. It's a little bit more performant. So I'm going to say from math, import square root. Okay. I could exponentiate to the 1/2, but in this case, I'm going to just import square root. I think it's a little bit better. And I'll throw that at the top of the file. And so standard deviation, that's all that takes. That's all we need to do to get a standard deviation function is take the square root of the variance. So now how do we apply this? Or how do we start applying it? One way is, well, the way that we'll think about this is through just an example problem. And we've seen this problem already, but in a slightly different form. Okay, an issue of a recent magazine has these house sale amounts for houses in Alameda. And remember, some of these look like outliers, blah, 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 right? We know what's going on in here. Find the variance of the homes, find the standard deviation of the homes, and if we exclude the values we consider to be outliers, do you think the variance will increase or decrease? And we can check the answer by making the calculation. So let's go ahead and walk through this. Put this up here. And we'll need that data, which should have somewhere in this. Is that the same? 615. That looks the same. Okay. Okay. So here we've got our house prices. The first thing we're going to do is we're going to find the variance of these homes. So find the variance. I like to think of the variance in relation to the mean, so I'm also going to print. I'm going to print the mean when I do this. That's, because when we're performing these analyses, we kind of want to see everything, right? So let's take the mean of the house prices and mean house prices. Sorry, let me try to troubleshoot this question really fast. So you're getting unsupported operand type for int and none type. That's interesting. That might be based on what's going on with your mean function. Do you want to paste in your mean function as well? You don't have a return statement in your mean function. That's what's going on there. So I'll just put in the correction there. Notice you just need to return the result. Currently, it's not returning anything. It's returning none. That's why you're getting that none type error. Okay, so let's continue with this. Okay, so we're printing the mean, and the next thing, obviously, we want to print the sample variance. We're assuming sample variance here, and let's call it samp var, and we're going to get the variance of the house prices that we have defined, and obviously sample gets true, although I don't need to put that in there because we already have that as a default. I'm going to round this, and that's what we did before because we don't really need a bunch of decimal places in this. Maybe I could round it to one place, but I'm not going to worry about that. Okay, so we find the variance, and then the standard deviation is very similar to this. Do the same thing. Instead of variance, I'm going to change this to standard deviation. So that's a good start. Let's see what we get there. So we get a mean of 620.5, a sample variance of 64,141, and a sample standard deviation of 253. Now, what's generally helpful here with analyzing these things just in code like this is to print a sorted version of our data, or print a sorted sample of the data. I'm just going to print the sorted version of this so that we can see it in context. And I think this is fairly interpretable, okay? At least the standard deviation is. We can see that our mean is around 620.5 with a standard deviation of around 250. So, the way that looks to me, if you start visualizing these things, the way this starts looking is, okay, well, we've got our X bar here, and we're going, 250, okay? So we're going kind of like, right? Ending somewhere around there. Maybe even a little closer. So, okay. Maybe I'll use a different color to really try to say what I'm saying. Let's use blue instead. So we're going to, blue doesn't show up very well, does it? We're really looking at this like, okay, well, here's our X bar, and we're drawing this kind of spread. If we're going to draw it, we're drawing it around this. And to me, it looks like our inclusion of data points is much heavier on this side, right? And that's not necessarily a bad thing. It's descriptive, but we'll get a different idea. This will get a different picture if we remove some outliers. And again, not saying that removing outliers is what we want to do, but it's what we are doing in this problem. So let's go ahead and do that. So let's get those outliers. I'm going to just do something like this: house prices, no outliers, and we've got this remove outliers function that we can use. So remove outliers from the house prices. So we've got that. And then we can print the sorted version of that. We can take this. And in fact, I do not need to print this out up here. So we're going to get that. And now we can look at the mean sample variance and standard deviation of that. So I'm going to reuse all this code. Copy paste is your friend. You tend to make way fewer errors when you copy paste. Although in the learning phase, I think typing things out can be very helpful. Just to get that that muscle memory a little bit more. Oop. Okay, so let's see what that looks like. Oh, 218. Oh, I see what happened. Try that again. Object has no attribute copy. What am I passing in there? I might have an error somewhere. No? Try that again. Oh, I'm doing mean of print of sorted house prices. That doesn't make any sense. Okay, let's try this again. Let's see if I can correct that all in one go. Okay. Try that again. Okay. I'm going to round this mean. As well. And by removing outliers, I think it makes sense. We've tightened things up a lot, and our spread has become reasonably more symmetrical as well. Okay, so where is our mean? Well, it's right here. So there's where X bar sits. And our standard deviation is going to be, something like this. And something like that. So that is reasonably symmetrical. Now, is that better? Who knows? Who knows in this situation? We have to really think about the context of the problem. It's descriptive in a different way, and we can say, okay, well, when we remove outliers, we get this nice symmetry around the mean, which is what we would expect from a balanced sample from a population. Is that necessarily better or worse? I wouldn't say it's better. I would say it's a different description. So I just want to be clear about that. Okay. So that's a little bit of application of these things, right? What I'm going to suggest is, these algorithms that we've been looking at here throughout the centrality and measures of spread. These are, in some ways, these are good template algorithms for understanding different types of problems you're going to try to solve in code. You can root these in the real world, right? You can take something like, some series of numbers or some real data, and you can answer questions like, what is the variance and how do you interpret that? That's something that you can do pretty simply with these functions. If you find these functions confusing, I highly recommend you make digital flashcards out of them, and you try to write them from scratch a few times until it makes sense, until it's easy enough to do, right? Especially something like a median function, right? There's a little bit of complexity here, and it's not as simple as you would expect, or the 5-number summary, or what's another good one here? I think the the interfunction dependency that we see here with the 5-number summary, IQR, detecting outliers and removing outliers, right? Building up your familiarity with okay, there's this job that this code needs to do, and here's a way I can get it to do it. That, I think, is really good practice. It's a good thing to iterate on, to repeat, to do repetitions on, really, until you feel like you could code these functions from scratch. And if you can code them from scratch, then the concept itself is very understandable. I think a lot of people are balancing concept versus syntax, right? Where, I understand this concept, I don't understand the syntax. Or I understand the syntax, but the concept is lost on me. A lot of the time, you have epiphanies when you're coding some concept that you're seeing. Something will become apparent, become much more readily apparent in a way that can be a little bit surprising. You're like, I understand this in a really deep way, suddenly. I think that's an experience in data science in general, actually, where you dig into some data, and you're given that data by people who are maybe domain experts, or who don't really look at the data so much, but they operate in some other capacity. Like, let's say, an example for me would be, there was somebody who played lacrosse professionally, and had moved into imaging for lacrosse coaches, like live imaging and tagging for lacrosse coaches. And he handed off this data set of lacrosse video to me and wanted me to tag players in real time and, discern if a goal was scored, or, all these things. And I don't know anything about lacrosse. I'd never played it. In fact, I still don't really know about lacrosse, but I can tell you a lot about lacrosse. And that's kind of a strange thing. I'm not a domain expert in playing that game, but I am a domain expert in the analysis of, things that happen in that game from the standpoint of, imaging the games and discerning what's going on. So there's this thing that happens when you get into data, when you start analyzing it, when you're doing your exploratory analyses and things like that. You learn about a field in ways that the domain experts don't know. And that becomes vitally important in informing them, right? You're trying to gain insights, you're trying to make predictions, you're trying to do these things that they're not necessarily able to do without you. And so you develop this different but parallel domain expertise in something that maybe you didn't know anything about. So that comes through coding, right? That comes through the systematic analysis that you do through coding. So often I think just solving a variety of problems becomes really good. And since we have a couple minutes, we'll end a couple minutes early, but I want to show you, I know we talked about this a little bit. I mentioned this on the first day, but I really cannot overemphasize the importance of being good at Python for the DSI. That is the primary thing you need to be good at. And to get there, okay, you can study Python in our materials. That's great. There's a fair amount of repetition in there. There's different challenges. You can do those. You can do them over and over again. That's great. But what I'm going to really suggest for that is Code Wars. Okay, I'm really going to suggest this because you can go here and just do a ton of problems. You can do a ton of problems. So I'm here on the Code Wars dashboard, and I usually sort by popularity of the problems. right? And it's listing 6,000 problems over here. I'm going to tune this down to just the easiest problems, and I'll walk us through a couple of these. So 8KYU, I only care about Python here, so I'm just going to put Python as the language I'm selecting, and I'll leave the status as approved because people have done them, and I know that it should be doable. And then I'll look at kata that I haven't trained on yet. And here's one. This should be fairly easy. Generate a range of integers. Okay. Maybe it won't be easy, but it probably will be. So implement a function named generate range, min max step, which takes 3 arguments and generates a range of integers from min to max with the step. The first integer is the minimum value, the second is the maximum of the range, and the third is the step. The min should be less than max. And then I can click on train over here. And what this gives me is a space to code in on the right. Maybe I can make this a little bigger. Although this doesn't respond very well to increasing the size, unfortunately, but that's a little bit better. It gives me the space to code the solution. I could code my solution in a text editor first and paste it in. Usually that's a little bit better because this environment is a little bit not as friendly as my code editor. And then there are tests down here, okay? So what I usually do is I look at the example, if they have examples on the left, and then I look at the tests and I try to pass these tests. So generating a range from 1 to 10 by 1 should give me 1, 2, 3, all the way up to 10. So notice it's inclusive of the max, which is different from our range function. I think what I can do here is just, we know we want to return a list, so I'm going to return a list of the range from min to max by the step. But because our range function operates a little bit differently from what they're describing, I think I'm going to put max plus 1, and then I'll click on test, and then I get output over here. And it looks like I passed all those tests pretty easily. So I passed all those, and then if I click attempt, it'll do a bunch of random tests over here. So it passed 105 of them, says, yay, you did it. And if I click submit, it'll give me a couple points probably or something. And then it'll take me to this landing page. Notice somebody, other people have done basically the same approach. That's not the only approach to do it. There are other approaches, but in Python, you're probably just going to use a range function to do that. And then I usually, if I'm playing around with this, I'll just close that out. I'll refresh this page with the same parameters set, and notice it just got rid of that one that I just did. So strong recommendation. If you are having trouble getting, if you're having trouble with your time to code, and by time to code, I mean how much time it takes you to get some code committed and working in this class. Spend, do like 5 problems of these a day, for a while. Do the simplest ones, the easiest ones, which are level 8s, because it's really about these repetitions in your early stages. It's about writing code often, writing exploratory code. If there's a problem that you want to solve and you're trying to figure out how to solve it, try to use code to solve it. And if you don't have anything like that at hand, it is really about this. It's really about doing these kinds of problems. And, as we saw before, let's say I want to look at the easiest down to what we might expect you to be able to do for the DSI offhand, or at the beginning of the DSI. From 8s down to 5s, I'm seeing something like 3,300 and more like 3,700, right? There's a ton of problems here, and I really, really recommend practicing here and getting your time to code, just getting it faster, knowing how you might approach a problem sooner, with a little more speed. That's just a strong suggestion. Doesn't mean you have to do it. If you don't feel comfortable doing that at this stage, that's understandable too. but at some point, you'll need to get your Python. You'll need to be committing coding every day, and this is an easy way to get that practicing. So that's class for today. Stay on if you have any questions. I'm gonna go ahead and stop recording on